Hi everybody, welcome to our first lecture on planetary motion and how gravity sort of fits into all of this. Now you might think this is an odd time to be talking about gravity since we've been using it a lot throughout the year, but we've been really using it in terms of an acceleration more than anything, and when we talked about weight as a force, but really the idea of gravity itself we haven't explored. Now, interestingly enough, we've talked about a lot of forces, tension, normal, weight, all things like that. But in the end, there are actually only four true fundamental forces of the universe. And these are what they are in order of strongest to weakest. So the strong nuclear force, this is what sort of binds the nucleus together. Protons in the nucleus should really not be allowed to stay together there, but the strong nuclear force binds them together. The electromagnetic force is the next one down in terms of strength. And we'll talk later on in the year about electricity and magnetism and where these forces come together and how the two are intertwined. But also very powerful forces. And in fact, largely, when you stand on the ground, the real reason you don't fall through the ground has a lot to do with that electromagnetic force supporting you. So it is pretty powerful. Then there's the weak nuclear force. This has to do with neutrons and some other subatomic particles and how they sort of bind together and decay. So also a very, very powerful force. The last, and considered the weakest force, is the gravitational force. Now here's the interesting thing. The strong nuclear, electromagnetic, and weak nuclear forces actually all act on the atomic level, and gravity is almost ineffective at that moment. Yet gravity is what causes, for example, our solar system to form and stay together. It's what initially causes a star to first form. So what we would see as, in our mind, an extraordinarily powerful force is actually considered to be very weak in comparison to the other three. But that's the one we're going to explore. So how does gravity work? How does it really, really work? Well, it has a lot to do with Isaac Newton, who, quote, discovered gravity. Now, of course, first of all, an apple didn't really fall on his head. That's a bit of a legend. But it began with the idea of, and this legend came out of, Newton exploring the falling apple as he saw it fall from a tree versus what he understood about the moon's orbit around the Earth. Now, by Newton's time, it was accepted that not only did the moon go around the Earth, but the Earth went around the sun, which was lucky for Newton. They weren't, burning people at the stake for saying the opposite anymore. But Isaac Newton recognized that in order for the moon to go around the sun, there had to be some sort of centripetal force involved, some sort of force that acted on the moon towards the Earth at all times. And now he knew there wasn't a rope or anything attached to the moon. And so he recognized that this force was able to act without any real physical contact. So this is one of our first sort of examples of what we call action at a distance, the ability to apply a force over a distance without physical contact. It's pretty amazing. But what Newton really recognized, the big thing that he recognized, that not only whatever force this was that acted on the moon always pointed towards the center of the Earth, but that the falling apple itself, that when the apple fell to the ground, it wasn't actually falling to the ground. It was actually falling towards the center of the Earth. In fact, everything, because the Earth was a sphere, had to be falling towards its center. And so Newton said, well, whatever force this is that's pulling the apple to the ground, something I'm going to call the force of gravity, must be that same force that's acting on the moon. And that was a pretty big leap for the time to actually recognize that those were the exact same forces. And so Newton came up with what he called the ideas of gravity and how gravity had to work. So Newton's law of gravity is this. Every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. Now that's a lot, isn't it? Newton's always a little bit long-winded in his laws, but let's look at a couple things to try to understand exactly what he's saying here. First of all, with the idea of gravitational force is we need at least two masses to act on each other. So what he's saying is that whatever this gravitational force is, it's directly proportional to the product of the masses. So what he's saying that is, if mass goes up, then my gravitational force will go up. So for example, if I have a planet versus a star, the star is going to be able to have the ability to produce a larger gravitational force simply because it's much larger in mass. Okay, so the amount of these masses makes a difference to how much force they can apply to each other. But the other part that he talked about is the idea that it's inversely proportional to the distance separating them. Okay, and that distance we're going to call r most of the time. So r is simply how far apart are the masses. And what Newton was basically saying that as distance goes up, my gravitational force will decrease. They're inversely proportional, okay? But to the distance squared. Now this is a little more complicated. See here, if I double mass, then I automatically double the gravitational force. However, if I double my distance separating them, okay, well, inversely proportional, first of all, means I flip that, okay? So I take that 2 and I flip it, 1/2. But Newton says that the force is inversely proportional to the distance squared. So I've got to square that. So the result is that if I double the distance, I actually get 1/4 the gravitational force. So clearly distance has a larger effect than even mass. So let's see this more in a simulation. Okay, so here we have the Earth and the Sun. Okay? And you'll notice that when I click on gravitational force arrows, both of these vector arrows, first of all, they point at each other, and they appear to be the same size. Well, that's just Newton's law of action-reaction, Newton's third law, because the Sun must pull on the Earth and the Earth must pull on the Sun with equal and opposite forces. Okay? And of course that allows them to maintain this relationship at all times. Okay? They're always pulling in each other, and as a result, that much smaller planet orbits around that much larger star. Now, if I increase the size of the Sun, notice that that gravitational force arrow increases. Or if I increase the size of the planet, again, each one increases that gravitational force. However, if you change the distance, as you can see, that gravitational force vector decreases. Okay, so increasing masses increases the gravitational force, directly proportional. Okay, so if I double the mass of the Sun, I double that gravitational force. But changing the distance, as you can see, has a much larger effect on that gravitational force. So the greater the distance, the much smaller the gravitational force. So what this eventually led to is an equation for Newton's law of gravity. It looks like this. The gravitational force is something called G, big G, times the product of the two masses, m1 and m2, all divided by their distance squared. And again, what we have here is an example of something called action at a distance, the ability for one object to apply a force to another without physical contact. G. G is actually a very, very specific number, and it's called the universal gravitational constant. Now the interesting thing is that Newton knew that there was some sort of constant, but he didn't know what it actually was. He did some math to sort of allow it to sort of disappear in terms of his experiments. But it wasn't until about 100 years later, and a guy named Lord Cavendish actually fairly accurately measured what this universal constant was. And his measurement was so accurate it wasn't refined, I think, for another 100 years. But the universal gravitational constant has a value of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Now it's kind of an interesting unit there, that unit comes from the formula itself. In other words, g needs to have those units so that when you multiply by the two masses and divide by the distance squared, you end up with force in newtons. So anyways, you can see it's a really, really small number. But it's kind of important into the idea of how we calculate things. R. Now this is really important. When we talk about the distance between two objects, we're talking about the distance from the center point of the object to the center point of the other object. Isaac Newton, one of the things he often discussed about mass is the concept of center of mass. Sometimes you hear it as center of gravity. He's saying that, for example, a planet, you could consider all of its mass to be squeezed down to a single point located at the center of that planet. So whenever we're measuring distances in terms of gravitational forces, we have to go center to center. Now, to give you an idea of how weak this force could be in terms of two things, let's say we've got two people. One with a mass of, let's say, 40 kilograms. And the other with a mass of 50 kilograms. And they're standing 2 meters apart. And we want to know how much gravitational force do they apply to each other. How much do they attract each other? Well, gravitational force, G, m1, m2 over r squared. Okay, G. 6.67 times 10 to the minus 11. Their two masses, 40 kilograms and 50 kilograms, all over the distance, 2 meters squared. And that gives you a force of attraction, a gravitational force between the two of them, of 3.34 times 10 to the minus 8 newtons. Okay? Or in other words, a decimal and 7 zeros in front of that, an enormously weak force. Which is why, of course, when we walk around, we're not suddenly being pulled into each other everywhere we go. However, interesting enough, if you were to take these two people way out into deep space, set them 2 meters apart, and even that weak little force would eventually start to slowly pull them together. Now, as they got closer, the force would go up, and they would accelerate even faster. And then they would get closer, and the force would go up, and they would accelerate faster. And strangely enough, over millions and millions of years, actually tens of millions of years even, that's how planets can eventually form and stars can eventually form. Just these tiny little particles begin to attract to each other. But let's look at it on a sort of larger scale. So let's take one of our people from the previous example. Say the person who had a mass of 40 kilograms. And imagine how much gravitational force is applied to them by the Earth itself, okay, as they're literally sitting on top of the world. Now, when we apply the gravitational force equation, G m1 m2 over r squared, okay, well, once again, G is that 6.67 times 10 to the minus 11. One of our masses is our person. The other mass is the entire Earth itself, which has a mass of 5.98 times 10 to the 24th kilograms. Obviously, much larger mass. Now, distance. Well, you might think, well, I'm only sitting maybe 1 meter above the planet. But again, Newton said that if we measure distances in gravitational force, it must be center to center. So from the center of the Earth to the center of the person. Now the radius of the Earth, as I've given down here, 6.38 times 10 to the 6 meters. That's basically 6,380,000 meters. That's a long way. So if you're 1 more meter up, do you think it matters? No, not to 6 million. 10 meters? Still no. 100? I don't think so. 1,000 meters? Well, now we're starting to maybe get a little bit of effect. 10,000 meters? Yeah, a little bit more. Okay, so small distances don't really matter, but large distances will above the planet. So for r, we're going to just use the radius of the Earth, 6.38 times 10 to the 6th. But we got to square that whole thing. Don't forget to square that. That's the number one math mistake made here, is people forget to actually square that number. And we end up with a gravitational force of about 392 newtons. Okay? Much larger, of course, than the force between those two people. In fact, more than enough force to keep you sitting in that chair so you don't sort of float away from the Earth itself. Now, here's a course of an interesting experiment if you're curious to do. Let's take that gravitational force of 392 newtons, and I'm going to divide it by our person's mass, 40. You know what I get? 9.8. Oh, that's a familiar number, isn't it? And in fact, if we remember, Newton's second law says that F equals ma, right? So that if I divide a force by a mass, I should get an acceleration. Oh, acceleration of gravity. That's where that number really comes from. The fact that the Earth itself gives you a certain value. And notice it didn't really matter what the mass was. So we'll sort of see later on. So that's how gravitational force works. So as I just mentioned there, using the idea of gravitational force, we were able to find out what the acceleration of gravity would be sitting on the surface of the Earth. Now, we've been calling this the kind of gravity, the acceleration of gravity, things like that. But its real name is something called a gravitational field strength. One of the things that we'll find as we move along and talk about some of these more fundamental elements of the universe is their ability to generate something called a field. And a field is sort of a region in space where things will have a certain value. And that field varies everywhere. And as you get further from the Earth, that gravitational field, the ability of gravity to actually act on another object, will decrease. So the acceleration of gravity of a planet, or a star, or anything like that, or its gravitational field strength, is based on two things: the size of the planet itself, its mass, and then how far from the center of that planet, star, whatever it is you're actually going to be. And so this gives us a relationship that looks like this. G equals gm over r squared. Now, that didn't sort of really appear out of nowhere. Again, when we talk about the idea of any body, planet, anything like that, radiating out in all directions is this sort of gravitational field. Okay? But interesting enough, the field itself always acts inward. In other words, you can imagine these gravitational field lines that are always acting in on the planet. And if you consider the fact that the force of gravity was g m1 m2 over r squared. Okay? Now, the most common name we've been using all year for the force of gravity has been weight, mg. Well, notice that allows me to cancel out some sort of mass. And that leaves me with this relationship for gravitational field strength, gm over r squared. Now the question is, what m did I cancel and what m did I keep? Well, if you think about it, I can't cancel out the planet's mass here. It's the thing that's really developing this gravitational field. Okay, so never cancel out a planet's mass. The gravitational field is based on the planet itself. So the mass is just anything else that might be in that field. So whatever mass is falling on the planet, coming towards the planet, in other words, wherever the smaller mass is, doesn't seem to be relevant. Okay? But distance is a very relative thing. Okay? So distance is from the center of the planet to any location, whether it's the surface or tens of thousands of meters away, 100,000 meters away. That distance becomes very, very important. So little g, which we've called just gravity or the acceleration of gravity, is technically called the gravitational field strength. And again, a field is where forces will have a certain measurement. Now, this is going to be a very important concept right here. We're going to see this in electricity, we'll see this in magnetism, and right here in the idea of gravitation. One object creates a field. A single planet creates a gravitational field. A single star creates a gravitational field. Okay? But it takes two objects to make a force. Okay? So gravity involves one mass. Force involves two masses. One makes a field, two makes a force. So in other words, a planet will have this field, but no force will exist until some sort of other mass enters that field. And then based on where it is in that field, it will experience a force. One object makes a field, two objects make a force. So let's look at an example. Let's say I've got two things. I've got a satellite in orbit 500 kilometers above the surface of the planet, and I've got an apple 5 meters above the surface of the planet. And I want to know the strength of the gravitational field that each one experiences. Okay? Let's actually start with the apple. So the gravity of the apple would be g m over r squared. Okay? G, 6.67 times 10 to the minus 11. Mass. Now notice I didn't give you the mass of the apple because it doesn't matter. Okay? The only mass that matters is the Earth, the thing that is developing the field. 5.98 times 10 to the 24th. Distance, center to center. So from the center of the planet to the center of the apple. Now again, 5 meters above the ground is nothing compared to the actual 6.38 times 10 to the 6th squared of the Earth itself. And when you multiply that out, guess what you get? Well, what you should get, 9.8 meters per second squared. Okay? And again, the units of gravitational field strength is meters per second squared. That is the standard unit of gravitational field strength, meters per second squared. Okay, well, kind of already knew that, didn't we? So again, any object that is near the surface of the Earth experiences that gravitational field. But what about that satellite? Now, before we get started with calculating out the satellite, there's something we're going to need to know, and that is r. R is going to have to be the radius of the Earth plus the height of the satellite, because 500 kilometers is significant in terms of height. So you've got 6.38 times 10 to the 6th meters plus, oh, wait a minute, 500 kilometers. Oh, we got to convert that. That's 500,000 meters, or 5 times 10 to the 5th meters, well, scientific notation. So the r that we have to use here is actually 6.88 times 10 to the 6 meters. That is this entire distance, center to center. That's the r we need. Now we can calculate our gravitational field that the satellite is in. 6.67 times 10 to the minus 11. Again, the only mass that matters is the Earth. It's generating the field even out at that distance. 5.98 times 10 to the 24th. And now my new distance, 6.88 times 10 to the 6th, all squared. And that gives me 8.43 meters per second squared. Well, that's interesting. That's not that much weaker than the gravitational field that the apple is in. And yet a lot of times we see these things where people are sort of in satellites, like up in the space station, and they're floating around in there as if they're in zero gravity. Well, it turns out they're not in zero gravity. There must be something else at play. We'll talk about that a little bit later. But as you can see, the gravitational field strength of the satellite is weaker than that of the apple. So again, gravitational fields exist based on one object, but there will be no force until a second object enters that field. So in that previous example, anything 5 meters over the Earth experiences that acceleration of gravity, 9.8 meters per second squared, regardless of its mass. But the force it experiences will differ based on each mass. That's why we all weigh differently. That satellite up there in space experiences that gravitational field strength as any object would. Okay? But again, the forces would be different if the masses are different. So that's basically an introduction to the idea of the gravitational force and the gravitational field. Okay? Again, both involve this universal gravitational constant, the big G, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. In gravitational force, it's directly proportional to mass. As mass goes up, so does force. As mass goes down, so does force. But inversely proportional to distance squared. So again, if you were to triple the distance, you would actually get 1/9 the force. Okay? Equally, if you were to cut the distance in half, you would actually get 4 times the force. Okay, got to invert it and square. All right, see you next time.